Good evening and welcome to this evening's session on program evaluation and the review technique. I hope that you will find it interesting and I hope that you would enjoy it. So let's have a look what it's all about. First of all, we're going to look at what PERT is and how we can use it. So if we look at PERT, how it can help us, that's the first thing we'll look at. Then we're going to take a look at exactly what do we mean when we are talking about PERT. Then also the two places that PERT can help us. First of all, we're going to look at how do we apply PERT in our estimations at activity level, and then also we're going to look at how we apply PERT in our estimations at project level. In other words, if we look at our critical path, what would be the impact over there? So how can PERT help us? What is the reason why would we use PERT? Now, first of all, if we look at our estimates on our project, we've got time, we've got cost estimates, we've got resource estimates, risks, and other estimates also on our projects. Now, these estimates are approximations. We cannot say 100% with certainty how long it's going to take us, how much it's going to cost us, how many resources do we need. So they are basically our best guesses with the information we have available at that stage. The estimates, therefore, are subject to a certain amount of uncertainty. And obviously, the more uncertainty that there is, the less accurate our estimates are going to be. And the less accurate that our estimates are going to be, obviously, our higher our risk is going to be that we're going to be either over or under the time frame, or over or under the cost, or that we have not taken all our risks into consideration. So PERT helps us to try and address these uncertainties, to determine how much uncertainty do we have, and also then to have a look what we can do about that, how we can address it. If we look at what PERT actually is, it's a technique, and it's a technique that helps us to take the uncertainty that we just talked about into account when we are compiling these estimates, hopefully realistic estimates on a project. So as far as risks are concerned, once we are estimating, identifying and estimating risks, is there uncertainty? Sure, there is. The definition of a risk is an uncertain future event that, if it would occur, could have either a negative or a positive impact on one or more of my project objectives. So there is uncertainty. If we look at time, we're estimating our time. If we look at the different durations of activities, there are a fair amount of uncertainty as far as that's concerned. If we look at the total time for a phase or a project as a whole, there is uncertainty as far as that's concerned. When we estimate our costs, we do our calculations, we do our estimates, but certainly there is still some uncertainty that we've got on that. The same with our resources. On the one side, we estimate which type of resources do we need, how many of them do we need, but it's also not to say we're going to get it, and it's also not to say that is exactly the number of resources that we need. Also, when we are looking at our risks, we calculate the probability of the risk happening, and that probability is not something that we can determine with absolute certainty. There's an uncertainty factor in that, as we also have with the impact if that risk occurs on our project. That's also an estimate, so there's uncertainty in that also. And we're going to look at how PERT can help us to combat some of this uncertainty. So if we look at what would happen, or what happens, if we only have one value of estimation, and we use it quite a lot on projects where we only determine one value. If I have to ask how long does it going to take us to travel between Earth and Mars, you have to do an estimate of the time. Then the most probable answer that we get back, and that is that, well, it depends. It depends on different things. Now, what does it really depend on? Obviously, it can depend on the speed of the launch. It can depend on the alignment of Earth and Mars, how far they apart at that specific stage, because their orbits do bring them closer and further apart from each other. And then also it will depend on the length of the journey that the spacecraft is going to take. As we know, the spacecraft does not always fly in a straight path. It might use Earth or something else as a slingshot effect to get to Mars. But if we look at what the normal time frames are for a journey from Earth to Mars, they normally say it takes between 150 and 300 days. And that is the uncertainty on that factor of where it's going to lie. If we, in a case like this, have to make one estimate, then we would find that that estimate we're going to make is going to tend to lie closer to the 300 days to make provision for the uncertainty. But if we keep on doing that on all our activities or on all our phases on our project, we can, at the end of the day, build in so much fat into the project that the time frames can become fairly unrealistic. So PERT, to come back to what PERT is all about, it is a weighted 3-point estimating technique, and it considers estimation uncertainty, and it also considers risk, and it uses 3 estimates to define an approximate probability for an activity's cost duration. So it is definitely not a technique that only uses one estimation. It takes the 3, and the 3 that it takes is, first of all, we will look at what is the optimistic, our best case scenario. What's our optimistic, either our cost or duration estimate what we're going to do. It also looks at what would be our most pessimistic one, the worst case scenario. So if we look at the worst case, what would our cost or duration be, the estimates depending on our worst case then. And then also what we need to take into consideration is what is our most likely one. And the most likely one that we work on, that's based on a realistic effort assessment of the required work that we are going to work. So once we have got those 3 figures, we can start using them to apply in the formula to determine what would be the best possible estimation for that specific activity or for that project we're talking about. So what is the formula that we use? The formula is that we would take one of the optimistic estimates, we'll take 4 times our most likely one, and then also 1 times our most pessimistic estimate, and divide it by 6. So it's weighted towards the most likely. There's 1 optimistic plus 4 most likely, that gives me 5, plus the pessimistic 6, so I get the mathematical average of the 3 estimates weighted towards our most likely estimate. If we bring that back to practice, and let's assume that we have obtained the following 3 estimates for an activity. So that's activity A. Optimistically, we have made an estimate that it can take us 5 days to complete it. Worst case scenario, pessimistically, it can take us up to 15 days. And we've also estimated that on average, most likely, it takes us about 7 days. Using our formula that our estimate, the PERT estimate here, is the optimistic plus the 4 times the most likely plus the pessimistic over 6. That gives us for optimistic 5 plus 4 times the 7, that's our most likely, plus 15. Now, adding those figures together, all 3 of them, we would find that it gives us 48 divided by 6. So our estimate for this activity A here would be 8 days. Now, how can we use that information? So before we look at how we can use it, we must look a bit about the logic behind this. So if we look at a normal bell curve or a normal distribution, a bell curve, we are assuming a perfect bell curve here, then we'll see that if we plot a large number of randomly occurring instances, we would find that the majority of these instances tend to be close to the mean. And as we go further to the pessimistic or the optimistic side, we see that it gets less and less. And if we look at this statistical information and we calculate our sigma or our standard deviation, and we'll see just now how we do it, then we'll find that statistically it can be proven that 68% of the population would lie between -1 sigma to +1 sigma. That's what we call our 1 sigma range. We'll also find that 95% of the population would lie between -2 and +2, so our 2 sigma range. And the 3 sigma, that would be 99.7%. So if we look back at our practical example and see how that applies, then we would see that our mean that we've determined, we looked at that case or that activity where we had the optimistic of 5 days, our pessimistic of 15 and our most likely of 7, and we calculated our estimate, and that would be our mean. So the mean is 8 days here, but we also need to calculate our standard deviation, and that's our uncertainty. And now where do we get that from? Our standard deviation is our pessimistic estimate minus our optimistic. In this case, 15 minus 5 divided by 6. So that gives me 10 over 6 or 1.67. So back to my bell curve, I'll see that from the mean to +1, that will be 1 plus 1.67 days, and to the other side, from the mean to -1, that will be minus 1.67 days, and so forth. We can continue on the next standard deviation and the next one. Taking that information that we have calculated just now, and we apply it to our project, we will see if we calculated our activity, the mean, as 8 days, and we now subtract 1.67, that brings us for 1 sigma, that its range will be from 6.33, and on the other side we add 1.67 to the 8, so it will be to 9.67. So what we are saying is, with the uncertainty in this project, there is a 68% chance that this activity will be completed between 6.33 and 9.67 days. If we keep on going further, from the 6.33 we subtract another 1.67, that brings us to 4.66, and if we add another 1.67 to the 9.67 on the other side, that takes us to 11.34. So what we can say, and that is that there is a 95% chance that we would complete the activity between 4.66 and 11.34 days. And if we go to our 3 sigma, 99.7% chance that the activity will be completed between 2.99 days and 13.01 days. So that helps us quite a lot to see what the probability is of falling. And in project management, we tend to work with 3 sigma most of the time. So we're working to a probability level of 99.7%. That still gives us 0.3% that we can either be under the 2.99, that's highly improbable, or that we can be over the 13.01 range. Now, that goes for if we look at activity level, but we know that the activities can be either over and under. Now, if we look at a critical path, if we look at our network diagram that we've got here, and we've got activity A, B, C, D, and E here, they are on a critical path, and we've got some other activities also, but they are non-critical activities, so they do not determine the duration of the whole project. if I now want to see what the impact is going to be on those critical path activities, I would find that we have got the estimate of 8 days for activity A. If I look at the information for that for activity B, optimistic 3 days, most likely 6, and our pessimistic 12. If we apply the PERT formula, you'll see that we get an estimate of 6.50. The same, if we calculate it for C, we will get a PERT estimate of 14, and for D, we get a PERT estimate of 25, and for E, 6.83. Adding them all together, that gives us a total duration for this project of 60.33. But that means also that there is uncertainty, and there's uncertainty we might be over or under of the different ones. If we look at A, as we said just now, we calculated this sigma as 1.67, and that means that if we looked at the 3 sigma and the -2 and the -1, so that was a -3 sigma was 3 up to, or 2.99 just now, just rounded it up, between 3 and to the other end between 13, and then the 2 between 4.67 and 11.33. We can do the same for B, and we'll see that for B we calculate our standard deviation or our sigma as 1.5. That means if we want to calculate the uncertainty, and if we want to calculate 1 sigma, it'll be 6.5 minus 1.5. Therefore, if we look at 1, 0 over there, we'll see that gives us 5. On the other end, we will add 1.5, that takes us to 9.5. Now, we can do that for all the activities. The problem is that we do not know which activities are going to be over and which are going to be under this mean. And we need to find a way of taking that possibility into consideration. So we know that there's a probability that any of these activities can take longer or shorter. So as we saw just now, A would be anything here between about 3 and 13 days. But because we do not know which activity is going to take longer, which is going to take shorter, we need to come up with a formula or a way of taking that into consideration. If we accept that some of them are going to take less, some of them are going to take more, then we can come up with a formula to calculate that. And it also means that I cannot just add all of them together, because that will give me too much of a deviation, in which case I will have unrealistic sigma values. So one of the ways of doing that makes sense, is that we say to calculate, now this is for the critical path, to calculate this sigma or standard deviation for the critical path, we are going to take the square root of the sum of the individual standard deviations, and then we're going to first determine the square of each and every one of them, and then we're going to calculate the square root of the sum of all of them. So what I'm going to do is I'm going to take my standard deviation for the first one, in this case A, multiplied by itself, plus the standard deviation for B, 1.5, multiplied by itself, and so forth and so on. Add all of them together, and then we determine the square root of that. And that would give us a much more realistic standard deviation for the critical path. So in practical terms, it's normally easy that we first calculate this, what we call the PERT variance, and that's nothing else that we are going to calculate the standard deviations squared. So if we calculate all of them, then we can add them all together, and then we can get the square root of all of them. So if we look at this example over here, first of all, there we've got our A, B, C, D, and E, and we have got our PERT estimates. We add them all up to 60.3 days, and we've got our different sigmas there. Should I just add all of those sigmas together, that would give me 5, 6, 7, 8, 9, 10, 11, 12, about 13 days. And if I would say that this project is going to come in at 60.3 days plus or minus 13 days for 1 sigma, then I am definitely over-calculating. So to use the other formula, the more realistic one, we would say that, okay, the PERT variance, in other words, 1.7 times 1.7 gives me 2.8. 1.5 times 1.5 gives me 2.3. For C, the PERT variance will work out 2.7. 2.7 is 7.1. D, 5 times 5, obviously 25. And then for E, 2.2 times 2.2 will give me 4.7. If I add all those figures up together, the 2.8, the 2.3, the 7.1, 25 and the 4.7, that gives me 41.8. If I now determine the square root of all of that, of 41.8, that gives me 6.5. And that is a realistic figure to work with, taking into consideration the uncertainty of each and every one of these activities of the critical path, but also not double counting to get an unrealistic figure at the end of the day. So if I would use that information now on our bell curve over here, we have calculated for the critical path that the mean is 60.3 days. We have calculated our standard deviation as 6.5 days. So what I could say, if I take the 60.3 minus 6.5, that'll take me to 53.8. If I take the 60.3, the mean, and I plus to the other side 6.5, that takes me to 66.8. So we can use this now to determine that there's a 68% probability that the project will be completed between this 53.8 and 66.8 days. You can also say that there's a 95% probability that we're going to complete the project between 47.3 and 73.3 days, and a 99.7% probability that we will be able to complete the project between 40.8 and 79.8 days. And that is handy information to have on a project, to have a way of determining the probabilities that we would be able to do to reach certain targets. Obviously, we would realize that it depends on the quality of the information. It's built from the initial estimates of the optimistic, the most likely, and the pessimistic. So we should build this on the most realistic figures for those to get a realistic figure at the end. So if we now have to do a quick test, and we look at the first one, if we say what would be the probability of the project to be completed on 60 days, and that is, in other words, on the mean of the project, and the probability to do that would work out to 50%. Now, why do we say it is 50%? We are assuming a perfect bell curve, and in a perfect bell curve there will be just as many possibilities to the left of the mean that there would be to the right. So there's a 50% chance of landing on the mean. If we look at the probability that we will complete the project within 66 days, then we can go and see where the 66 lands, and 66 days falls within 1 sigma, because 1 sigma is between 53.8 and 66.8. So we could say there's a 68% probability of completing this project within the 66 days. Going further with that, if we would say the 73 days, that is 2 sigma, so that falls within the 95% chance of completing it. And lastly, if we look at the probability of doing it within 97 days, that means that we've got a 99.7 chance or probability to complete it within 79 days on that one. Okay, are there any questions on this? Anything else you would like me to discuss or to explain about it? Okay, if nobody has got any questions, this short webinar was videotaped, so should you require a copy of this to go through it at a later stage, you're more than welcome. You can contact us and we will give it to you. Good. Thank you very much for partaking in this webinar, and I hope that you enjoyed it, and I hope it was something of value for you. Good night.